Hi, I'm Brian. In this video, we'll be looking at the Impact Computing Project. We'll be talking about how to start this computing project, the structure of the template code, and how to implement Contact into this computing project. So first of all, I'd suggest looking at your old Contact code from the Contact Computing Project and review how we implemented Contact into that CP. But make sure to download the template code for this computing project on Blackboard and actually use that to build this computing project. Okay, let's go ahead and look at the template code that's given. So first off, we have our problem data. Notice that we now have 2 of everything for each of the pendulums. The pendulums will be completely independent of each other except for during the contact phase. We have initial conditions for both pendulums as well. Here we're going to define some intermediate variables that don't depend on time. This is going to make the rest of the code much cleaner and easier to debug. I recommend doing this whenever you can. And if you run this computing project with the movie code turned on, then you'll see the template code does everything except for detect contact, which is your job to implement. All the numerical analysis parameters will be the same as the previous CPs as well. And the history array will work as is. Notice that now we have a vector containing the angle and angular velocity of each pendulum. This means when you want to grab theta 1 or theta 2, you have to use this syntax, xold of 1, xold 2. Similarly for vold and vnew, you're going to have to grab the corresponding entry. And then here we're going to initialize our acceleration. And we're just going to go ahead and skip to where you're going to have to implement contact. This slide from the computing project notes is going to be the most important, so we're going to take a look at this right now. We're going to go ahead and focus in on case 1. So the first thing that you're going to need to do to detect contact is to calculate these quantities highlighted in blue. And note that these superscripts are not powers, but indicators of whether or not we're talking about pendulum 1 or pendulum 2. And the subscripts indicate if it is the current or last time step. N plus 1 indicates the current time step, and N indicates the last time step. Also note that when you're computing F1 old, F1 new, and Z2, you will be using the dot product and not matrix multiplication. So you'll have to use in the built-in dot command for MATLAB. So after we compute these quantities, we're going to go ahead and actually detect whether or not contact is occurring. So for case 1, that's going to look something like this. And note the MATLAB syntax on the right. We're going to use the and symbol. This means that all of these conditions must be true in order for contact to be detected. If contact is detected, then we can go ahead and interpolate. This is what we'll use this zeta1 variable for. And in the notes, we also are going to describe how to interpolate based on the values of the function. So go ahead and look at that. You're going to want to interpolate before you actually update your velocity for the time step. And the last thing you'll want to do in this if statement is actually update your velocity for after impact. So in the blue, we have what you're going to want to enter, and then up in the top right, we're going to have the full equation. We use this capital theta term as another intermediate variable to keep things a little bit cleaner. And looking at the full equation, we have the coefficient A, vnew, B, and vnew. Once we compute the values of the A matrix and B matrix, we can actually use MATLAB's built-in solver command. That's the / command. So we can use vnew equals A / B times vnew, and that's going to give us the velocity after the impact. You'll want to follow the same process for case 2 as well.